Hello? Does it? Yeah. Okay. I guess this is better. Okay. So that means that the early universe is sensitive. Well, we have very high energies here in the early stage. It's much higher than what we can ever realize in a human-made experiment, right? So therefore, we have a kind of a particle physics laboratory here at extremely high energies. Now, of course, we can't directly put detectors here into the Big Bang. We do have observables from this time, and these different slices here show us different observables that we can use to look at things. So here we have optical astronomy, then we have microwave astronomy. Before that, we can look at the light element abundances in the intergalactic medium, which were formed in primordial nuclear synthesis. And from even earlier times, we might in the future have the cosmic neutrino background or the gravitational wave background, hopefully to probe even earlier times, okay? And of course, we believe that CMB perturbations were created at some very early times, giving us access, well, to these very early times. And conceptually, the way how I, as a particle physicist, look at this is basically, we here have some very, very high energy state that is composed of elementary particles, and many properties of the cosmos that we observe today were shaped by non-equilibrium quantum processes that took place at this early stage, and that when they'll shape the universe that we see now. And concrete examples for that are inflation and reheating, the formation of dark matter barriers, and baryogenesis, primordial nuclear synthesis, and so on. All right? So directly particle physics processes up here shape the universe over there. Now, in order to use that empirically, we need to be able to make theoretical predictions from this period. And the sort of canonical method to do so is the so-called Boltzmann equation. So if you read Kolb and Turner, you will know the Boltzmann equation. And the Boltzmann equation is semi-classical in the following sense, as it basically assumes that particles propagate freely like classical free particles between isolated collisions. So these collisions here, they are described with S-matrix elements obtained from quantum field theory and vacuum. And in between the collision, we assume that we have asymptotic state, that is, so to say, free classical particles. Okay? Now, there are several shortcomings of these descriptions, and I'm going to, one of my field of work is sort of related to how trying to overcome these shortcomings. First of all, this description works very well for many processes, for example, the CMB decoupling or BBN. But there are some conceptual shortcomings that I've kind of tried to illustrate with this schematic Feynman diagram. First of all, whenever you have coherent and decoherent, but coherent, let's say, effects, for example, neutrino oscillations, it is not captured by the Boltzmann equation in its canonical form. Oops, wrong direction. Because the neutrinos between two scatterings, they would perform coherent quantum oscillation, and that is just not captured by the asymptotic state. I keep on getting confused. All right. Here, then, quantum statistical effects. So you can, in the Boltzmann equation, you can put Bose-Einstein and Fermi-Dirac equations for the particles in the external legs, but for the internal legs, quantum statistical effects are not accounted for by the standard Boltzmann equation. Moreover, the particles that are inside here, they will also be screened by the plasma. They will typically be screened into quasi-particles. And not only the properties of the existing particles are modified into quasi-particles, you can also have new collective excitations of the plasma that act as quasi-particles. And you can have non-perturbative effects that I'm going to come to. So all of this means that ideally you would not use the ad hoc Boltzmann equation, but sort of derive suitable quantum kinetic equations to describe any given process in a systematic way from first principles. Okay? And I will talk about two examples of applications of this formalism that I'm of formalism. And the two examples that I choose happen to be inspired by Professor Sasaki's talk the day, no, it was yesterday. He said the two things that were not so well understood are reheating and the creation of the baryon number. So I will talk about these two processes, okay, and how to describe them in this way. But first of all, on a general level, how do I want to overcome the shortcomings of the Boltzmann equation? And basically by means of quantum statistical mechanics, or better to say, non-equilibrium quantum field theory. So instead of thinking about asymptotic states, I can think about the density matrix, von Neumann density matrix, which is an infinite dimensional matrix. Well, instead of looking at the infinite dimensional matrix that appears in the von Neumann equation, I can look at correlation functions, 1 point, 2 point, 3 point, 5 point, whatever, endpoint correlation functions with some quantum statistical average, where the trace here constitutes an average over quantum not only the usual quantum average that you would have in vacuum, but you can evaluate in any kind of statistical state. So it's quantum and statistical average. Okay? And then you can express all observables in terms of correlation functions, and you can derive equations of motions for those correlation functions. These will usually be non-Markovian and very difficult to solve if you want to do phenomenology, but you can derive from that effective quantum kinetic equations in a series of controlled approximations. So which controlled approximations you have to make, of course, depends on the specific problem that you want to solve, okay? It's not always the same, depends on the situation you look at. All right, okay, and there's a long history of doing this. Of course, I haven't invented this. This started in the 60s with Kadanov and Baim and Schwinger and Keldysh. And so just since I'm in China here, I'd like to remark, when I was a graduate student, one of the sources of literature that I learned a lot from was actually this review here, which was written, well, I think 1986 here in ITP in Beijing. So yes, there's some credit to the people who drove this field here in Beijing. All right, so then I promised I'm going to talk about two concrete examples. And the first example that I would like to talk about is the question, how hot was the Big Bang? Or in other words, how to reheat the universe after inflation. And can we learn anything observational about this process? Okay? So we have seen these pictures in Professor Sasaki's talk yesterday, and also this morning Professor Ahn showed this talk, already. We have the standard single field inflation picture. So we have the cosmic microwave background, and the perturbations in the cosmic microwave background are typically generated during the inflationary stage. And the inflationary stage is driven by the potential of some scalar field. As long as the scalar field sits up here and rolls slowly, it basically behaves like dark energy, because it's almost constant and it's like a dark energy. But in contrast to a cosmological constant, at some point the field reaches the end of this potential and down here and starts oscillating. And in this period of oscillations, all the particles that we know are produced in a process called reheating. And schematic, in some approximation, one can describe the whole process with this equation, where this V is the effective potential and this gamma is the dissipation coefficient that describes the particle production here. And of course, the range of applicability of such an equation is limited, and I'll get to that point in a second. The observationally relevant question is that here the CMB perturbations that the primordial CMB perturbations are produced during this stage, as we learned yesterday. But what we observe, we are of course here, and in between that is the reheating phase. And during the reheating phase, the universe continues to expand, and this expansion affects the redshifting of these rates, and that leaves an observable imprint in the cosmic microwave background. And I'll try to illustrate that with this picture here. So what you show here in the x-axis is the scale factor, so the size of the universe in some sense. And this here is the horizon. And this is some co-moving length scale. So if you're in physical coordinates, you would say the horizon during inflation is constant and the modes are getting redshifted. But if you look at co-moving coordinates, then the length of the mode is constant, and what instead happens is that the horizon changes relative to that length. Okay? And then you can see this is sort of for two different, we are somewhere here, we're trying to reconstruct backwards what happened, and depending on what we assume, let's say, the slope, the slope here in this plot is determined by the equation of state in any given period. So we have lambda domination, then we had matter domination, radiation domination, and during reheating, in general, the equation of state is neither the same as inflation nor than radiation, so it's different. And here you see, depending on how long the reheating period was, you come to different conclusions on when a mode that you observe here now would have crossed the horizon inflation. That affects how you reconstruct model parameter from observation, because like so the length of this reheating period is governed by the efficiency. Okay, here we have this dissipation coefficient. So the length of the reheating period is governed by the efficiency of this reheating. The larger gamma, the shorter is the reheating period. The more efficient the universe gets reheated. And the shorter the reheating period, the earlier a given mode would have crossed the horizon. And that affects the so-called slow roll parameter that you infer, and therefore affects the spectral index that you observe, and also affects R. So therefore, CMB is directly sensitive to the slope and the length of this line, or in other words, the equation of state during reheating and the duration of the reheating epoch. What can you learn? Oh, yeah, that we had already. So what can we learn from this? We can learn from this two things from the empirical viewpoint. The first thing that we can learn is this blue box here. Because the CMB is affected by the duration of reheating, and because the produced particles, so the duration of reheating, also determines the so-called reheating temperature. Okay? Because the longer reheating takes, the more the energy density of the universe is redshifted during reheating. And that is, if I can constrain the duration of reheating in this way here, then I basically constrain the reheating temperature. Because the longer your reheating takes, the more the energy density of the universe gets diluted during reheating, and the lower the temperature at the beginning of the radiation-dominated epoch in cosmic history is. So therefore, this effect allows us to probe the reheating temperature. So this is step number one. But there is another thing, we can go one step beyond that, if we are lucky, because this dissipation parameter here is governed by the interaction of the inflaton with other particles. And that gamma in principle is calculable from fundamental interactions of the inflaton. So this gamma is a function of the inflaton coupling constants. So therefore, by constraining gamma at the end of reheating, I can also learn something about the microphysical parameters from which this is calculated. Therefore, I can learn something about the inflaton coupling, or in other words, about the connection between inflation and particle physics, about the embedding of a given inflationary model into a particle physics theory. Okay, so I can probe some microphysical parameters at very high energies this way. Okay, good. So far, so good. The problem is that practically calculating this gamma is not always easy. And for the present of this discussion here, when I talk about microphysical parameters, I'd like to classify microphysical parameters in three different categories. This is very useful because when we observe the CMB, we only have a limited number of observables. In this case, I'm using the normalization of the scalar perturbations, the spectral index, and the scalar to tensor ratio. And we can only constrain a limited number of parameters if we have a limited number of observables, right? So let me introduce three different types of parameters. So first of all, these, what I call the VI, are the coefficients in the inflationary potential. I can just expand that. So all of these are fixed once I fix my inflationary model. Then I call the G are the coupling between the inflaton and other particles. And then there are all other couplings, these which I call the A, which are how all other particles interact with each other. These, for example, include all the standard model particles. Now, if I want to constrain microphysical parameters from reheating, I know that this gamma parameter, here, always the wrong way around, that this dissipation parameter here that I'm sensitive to, it necessarily depends on these interactions between the inflaton and other particles, because that's what drives the interaction. But ideally, if I want to extract the information about these parameters from reheating, then ideally, this gamma should be independent of these AI, because otherwise, of all the other parameters, of other interactions of the produced particles, otherwise I don't have enough observables to constrain the parameters, right? So let's get back. So the first question, what is the reheating temperature, doesn't rely on these considerations. That I can just, once I know the duration of reheating, I know the reheating temperature. The second question, whether I can convert that into knowledge on microphysical particle physics parameters, that depends on whether or not this gamma is in principle calculable from a small number of parameters, small enough that all of them can be fixed by observation, by data. Okay? Good. Now, yes, so I said I want to. So when it comes to the calculability of this gamma, I try to take this first principles approach that I mentioned to see in which situation can I calculate this gamma reliably. In order to do that, I use the so-called closed time path formalism. And as I said, what is also sometimes called in-in formalism, I think Americans tend to call it the in-in formalism. The Stringer-Keldysh closed time path in-in is all the same thing. So I express everything in terms of correlation functions. And here I only consider 1- and 2-point correlation functions. So the 1-point correlation function is just the expectation value of the inflaton field, just kind of the background field. And then there is this object here, which is called the spectral function, the poles of which give me the spectrum of quasi-particles. And then there's this thing here called the statistical propagator that I can form. that gives me the energy density and the occupation numbers in the plasma. But in contrast to usual occupation numbers in the Boltzmann equation, this does not rely on the definition of asymptotic state, so it can be done inside the dense plasma, okay, where no asymptotic state exists, because particles are never far away from each other, okay? Good, and all other propagators can be expressed in terms of those, like the Feynman propagator or the Weidmann function, whatever. So the goal is to solve the equation of motions for these guys, and a very useful tool to obtain the equation of motions for these propagators is the closed time path. So when I say equation of motions for the propagators, you have to keep in mind that this is non-equilibrium field theory, so everything is dynamical, depends on time. If you're a collider physicist, then there is only the propagator. So the electron propagator is what it is in vacuum, period, right? You can write it down, it's in Peskin's book or in any other book. But here, the propagator is a dynamical quantity. It evolves with time because we're in a non-equilibrium situation. We want to solve an initial value problem, okay? So to get the equation of motion for these propagators, I can use this, people use this closed time path in the so-called two-particle reducible effective action on this closed time path. I don't have time to in full detail how it works, but I'm just sketching. This is how it works. And from this effective action, you can derive first the equation of motion for the mean field. From this kind of consideration, you form the functional derivative. And this equation of motion in general is non-local and has a kind of Langevin type. It's usually a non-Markovian equation. But there are some situations in which it can be Markovianized and transformed into an equation that is local in time. And in particular, it can be done in the slow roll phase when the derivatives of the field are sufficiently small when compared to some, well, let's say interaction time that has to be defined depending on the problem under consideration. And the other situation is when we are in a situation where the field when the evolution of the field is in what they call the mildly nonlinear regime, so approximately perturbed harmonic oscillator. So if we either have a very slow rolling field or a perturbed harmonic oscillator, the resulting equation of motion can be Markovianized and be brought into this kind of form. Now, during inflation and reheating, we happen to have precisely those two situations. We have the very slow roll here, and we have the perturbed harmonic oscillator near the minimum. In between, there is a period usually where none of these approximations holds, but since the effect that we are looking for the CMB is an integrated redshifting effect, the fact that there's a brief period in between where this doesn't hold is unlikely to change our conclusions, okay? So there's a bunch of work, some of them are own, some of them much older than mine, but much more senior people have contributed to developing this kind of ideas. But we don't only need the one-point function, the field, we also need the equations of motion for the propagators. And these are obtained also by functional derivative from this 2pi effective action. So you first get a sort of Schwinger-Dyson-like equation on this contour, and when you break that down into an equation on the contour, you can write this coupled set of equations for the so-called Weidmann function. These are correlators that I mentioned before. They're known as the Kardanov-Beim equations in condensed matter physics. And they can be brought into a particularly convenient form by adding and subtracting them from each other for this spectral function and statistical propagator. So remember, spectral function, the poles of the spectral function give us the spectrum of quasi-particles in the system, and the statistical propagator gives us the occupation number and the energy density, basically, in the system. Okay? Now what appears here on the left is a potentially, so this is here the time derivative. This is in Wigner space. You see it's a momentum and time. And this omega squared is a time-dependent frequency that consists of the momentum, then the tree level mass, and then the local self-energy. So do we have a, so what I mean by tree level mass, apart from the vacuum mass, is like if you couple to some background field, so if the propagator couples to the field phi, you get some local contribution that looks like this. And what I mean by the local self-energy, for example, if you have phi to the fourth theory, you would get this diagram. And what I mean by local self-energy, if you have phi to the fourth theory, would be this kind of thing, okay? So this is, now, if you do an expansion in h bar, so if you do an expansion in h bar, you can, for the moment, forget about, in this pi here, sorry, I forgot, in this pi here are the non-local self-energies. So that would, if you have phi to the fourth theory in mind, for example, correspond to diagram like this. Okay? Static sum. All right, so if you do an expansion in h bar, at 0th order, there is no, the right-hand side becomes 0 because this kind of diagram doesn't exist, but you still have the time-dependent frequency on the left-hand side because this kind of diagram exists even at tree level. Then you get an equation like this with a time-dependent mass, and as you know, probably know very well, this time-dependent mass leads to instability, so-called parametric resonance, and so on, that can lead to particle production. This issue has been studied for a long time by many people, and since the 0th order expansion in h bar, it's nowadays often done by classical lattice simulations by software such as cosmologists. Okay? And this is actually not work done by me, this is work done by these gentlemen here, where basically the reheating process is studied on the lattice, so in this classical approximation. And this is this is for 3 different magnitudes of the inflaton coupling, and this is time. And here you see the evolution of the energy density of the plasma of produced particles. So you start producing particles and they form a plasma during reheating. And here you see the evolution of this energy density. And so here is the blue is the perturbative approximation and the black is the lattice simulation. And you see for small inflaton couplings, they agree very well. So in particular, the perturbative description, well, at least here, captures the maximal temperature during reheating well, and it also captures the temperature at the end of reheating well. So if you make the inflaton coupling larger, you see that here the lattice simulation deviates quite a lot from the perturbative calculation during reheating, but it doesn't affect the end of reheating, because the end of reheating happens when this red line here is the inflaton energy density, and the black line is the density of the produced radiation. The reheating ends, by definition, when the radiation starts to dominate. That is when the black line crosses the red line, right? So here, so we can have two important things. One is what is the maximal temperature during reheating, and the second is what is the duration of the reheating. And for small inflaton coupling, none of them is modified. For medium inflaton coupling, the temperature during reheating is modified, but the duration isn't modified, because in spite of the fact that the black curves goes above the, so from feedback effects during this non-perturbative feedback effects goes above here, it doesn't change the duration of reheating. But if you make the inflaton coupling sufficiently large, then you see that this perturbative calculation, which doesn't include the fails to capture the dynamics. And there are strong feedback effects here from the produced radiation. So if you just do a naive perturbative estimate, you would get wrong not only the maximal temperature, but also the duration of reheating. So what does that mean from our ability to extract microphysical parameters here? So I said that there are these 3 categories of parameters. Basically, reheating is always sensitive to those, or those I want to constrain. But then there's this large number of other parameters. So whenever these feedback effects are strong and change the duration of reheating, then the CMB becomes sensitive to all of these parameters. And that means I cannot uniquely constrain those parameters anymore from CMB data. Okay? So if I want to only constrain the reheating temperature, I don't care. But if I want to constrain microphysical parameters, I would like to avoid a situation where feedback effects bring in dependence on all of these parameters into the duration of reheating. And that's precisely what happens here. So basically, it means I can't make the inflaton coupling too large. Okay? So I want to ask these non-perturbative feedback effects and parametric resonance, and so do not change the duration of reheating. Okay, and I can study this kind of semi-analytically by looking at the so-called instability bands of the Mathieu equation. And if maybe some of you have seen this before, these non-perturbative effects can qualitatively be described. So, okay, So, in this order here, the equation can formally be mapped onto the so-called Mathieu equation, and the existence or non-existence of this non-perturbative feedback effect has been pointed out long ago by these gentlemen, can be studied in terms of the stability bands of this Mathieu equation. And in order to avoid strong feedback effects, the first requirement, I want to avoid a broad resonance. So I want to avoid a situation where many momentum modes, as shown here in this sphere, are affected by the resonance, by this non-perturbative effect. So if I want to avoid a broad resonance, so I want only a so-called narrow resonance, so only a narrow band of modes should be unstable. Because if I have only a narrow resonance, then redshifting of these modes can make sure that they get redshifted away before they become too highly populated and feedback effects become strong. Okay? Good. So I impose, and I can impose these conditions in terms of the Q parameter that is commonly defined in the material equation. Good. Even if I don't have this non-perturbative effects, I can say, okay, let me briefly jump back. So this is the full set of equations that you want to study, and if I use the Mathieu equation, I can only study the left-hand side, sort of the zeroth order H bar part of this. But if I now assume I don't have strong feedback effects from the zeroth order H bar expansion, I still have these self-energies on the right-hand side, and I can calculate these, and if I do this at the approximation that the plasma during reheating immediately thermalizes, so then I can use thermal propagators to calculate those, and then for different types of interactions, I can calculate what is this rate gamma that appears here. So it can be well, scalar interaction, axion-like, U-cover, whatever. And you see, in general, these are relatively complicated functions because there's some part that depends only on this inflaton coupling G, let's say in this case, so the inflaton coupling. But then there is a phase space, which is affected by the effective quasi-particle masses in the plasma. Then there are quantum statistical effects. And this is only the medium modification that happens to the medication modification here, the Fermi blocking or Bose enhancement that happens to the decay. If you look at the full dissipation rate gamma, in general, it has a relatively complicated shape as a function of temperature compared to the inflaton mass. Because in the plasma, there's not only the decay that can contribute, but many different processes can contribute to the dissipation of the inflaton, and so to say, to the production of particles into this gamma parameter. That means, in principle, the efficiency of reheating, even if we don't have a parametric resonance that brings in complicated nonlinear behavior, all these thermal effects can also make things complicated and make it difficult to extract microphysical parameters from the CMB. Okay? Luckily, in most cases, what happens is that these complicated effects do not modify the duration of reheating. And recall, the CMB is only sensitive to the duration of reheating. It's not sensitive to the thermal history, so the temperature evolution of the plasma during reheating, because it's a redshifting effect that makes the CMB sensitive to reheating. That is, so if I look at the blue curve here, is without so this is the scale factor, this is the evolution of the temperature during reheating, here's the end of reheating, and here's the beginning of reheating. The blue curve is without, well, by just taking the vacuum decay rate, which is here, and the red curve, or always the wrong way around. The red curve is here. You see in the beginning of the reheating period, you have strong feedback effects like Bose-enhanced transitions make your reheating more efficient. But then the temperature drops because during reheating, the universe expands. And at the end of reheating, actually, there is no difference between the red and the blue curve. So these complicated, more complicated thermal corrections, quasi-particle effects, quantum statistical effects, they do not actually change the duration of reheating. And this is a relatively generic result. One can write down two conditions for these parameters in the inflaton potential and for the inflaton coupling to assure that these complicated feedback effects do not affect the CMB. Okay, there were a lot of technical details, and I hope I haven't lost all of you by now. The bottom line is that if these conditions, so these are the parameters in the inflaton potential, and these G are the inflaton couplings where I have parametrized any generic interaction that the inflaton might have in this way, where O is some operator in terms of other fields, and this is the inflaton at some power J. So for these, so this is the operator, a generic operator where the inflaton interacts with other fields, where the inflaton comes at power J, and this is the expansion of the potential. If these two conditions are fulfilled, then during reheating, there are no complicated feedback effects, and the effective dissipation rate during reheating can be expressed in terms of the inflaton potential and this one single parameter alone, which gives us a realistic perspective to constrain it from cosmic microwave background data. Okay? That's the take-home message. And for the plateau type of models that describe the data very well at the moment, we can actually find rather simple simplifications of these criteria. So here, these two criteria are formulated in terms of the inflaton mass and the inflaton field at the end of inflation. And here the inflaton mass and the Planck mass, so they are always determined by these ratios. And lambda here is some energy scale in the expansion. But specifically for plateau models, I can write down simple expressions for these agents on the right-hand side in terms of the amplitude of the scalar perturbations in the CMB and the scalar to tensor ratio. Okay? Of course, there's also a lower bound on the reheating, on the inflaton coupling. So here it means there's an upper bound on the inflaton coupling. If it's too large, I get strong feedback effects and I can't constrain it from observation so easily anymore. But there's also a lower bound because I need to actually reheat the universe. Because if I put the inflaton coupling to 0, there's no complicated effects, but I also don't reheat the universe, right? So there's a lower bound, upper bound. Okay? Now the question is, can we realistically observe this within, so can we have, in realistic models, can we have reheating in a range of couplings where these conditions are fulfilled so that we can use CMB data to constrain the reheating temperature and the inflaton coupling? And second as well, are there any realistic CMB emissions observations that can do it from a technical viewpoint? And in order to address these questions, I'm going to focus on two types of specific inflationary model. One of them is the so-called mutated, well, we did it for 3 models, but I'm only mainly going to talk about 2 of them here. So we did it for mutated hilltop inflation, for radio gauge inflation, and for the alpha attractor model. They all have very similar potentials. And the potentials have 2 parameters. The parameter m determines the height of the plateau here, which basically gives us the scale of inflation, the energy scale at which inflation happens. And then this parameter alpha basically determines how narrow this valley here is. So in other words, it gives us the mass of the inflaton particle, okay? And then there's a third parameter, which is the inflaton coupling to other particles. So in principle, we have 3 observables that we consider: the amplitude of scalar perturbations, the spectral index, and the scalar to tensor ratio in the CMB. And we have 3 unknown parameters that we want to constrain. For practical purposes, I will always have to fix this alpha parameter, and then I will constrain simultaneously the scale of inflation and the inflaton coupling from observation. And if I do that for this RGI model, I get the following picture. So this is the spectral index, and this is the scalar to tensor ratio. And then for each value of alpha in this, so for each inflaton mass, so to say, for each value of the inflaton mass, my model is restricted to a line in this plane. And where along this line you are depends on the duration of reheating. So the longer reheating takes, the further to the left you are. And what is written on top of these circles here is translating the position along these lines into a value for the inflaton coupling, assuming that it's a U-Carver coupling. So here it's 10 to the minus 5, 10 to the minus 9, 10 to the minus 12, and so on. Right, so here it's roughly like the electron U-Carver coupling. You can compare that to well, either Planck or Planck plus bicep data. What you see here is that current data doesn't actually tell us very much, simply because basically any of these values for the inflaton, for alpha, so say the inflaton mass can be accommodated for, and then for given alpha, the reheating temperature or the inflaton coupling can vary by many orders of magnitude within the 1 sigma region of Planck and bicep. Okay, so practically there's no constraint or very little constraint with current data. Luckily, there will be a lot of data in the future. So we have some CMB observations, CMBS4 and the LightBird satellite, and then there will be also 21 centimeter observations and, well, galaxy surveys that help us to further constrain this. And if you look at what can be done in the future, so this is the what I forgot to say, of course, sorry. The gray areas are excluded because here reheating would take a negative amount of time. That, of course, is nonsense. And here you would fail to reheat the universe at a temperature that is high enough to do Big Bang nucleosynthesis. Okay? Good. So what to expect from the future? Again, here we have the spectral index and the scalar to tensor ratio. And this is the Planck plus bicep constraint. The gray area, again, is the region where reheating takes negative amount of time, which is, of course, nonsense. And here on the left, you fail to reheat the temperature, the universe high enough to do Big Bang nucleosynthesis, which we know happened. And here you see this is what can be expected. The dotted black circle, well, ellipse is what can be expected in terms of improvement from Lightbird or CMBS4, roughly. And the red curves is what, so that's mainly corresponding to a measurement of R, assuming an R in this region here. And the red curve is what you get if you, in addition to that, put constraints that you can put on this on NS if you use data from SKA and Euclid satellite in the future. Okay, so this is the anticipated what can be achieved in the future, assuming that R is somewhere here. And then what learned about the reheating temperature and the inflaton coupling from this is shown on this plot here on the left. So here, this is the inflaton coupling, assuming a U-cover coupling reheats the universe. And up here is the reheating temperature. And so in this region, again, reheating takes negative amount of time, and here the reheating temperature is too low to reheat the universe. Then we put a flat prior and log space on this and do a simple Bayesian analysis, just assuming that a two-dimensional Gaussian describes this well. And if you do that, you find that this is the posterior, so you do simple Bayesian analysis of this kind, and just model this blob here with the Gaussian. If you do that, then you find that with Planck and bicep, as you can already see by eye, this is the posterior for Planck and bicep. Basically, everything is still allowed. But with Lightbird and CMBS4, this would be the posterior. So you can determine the reheating temperature or the inflaton coupling from this data with well, there's an upper and a lower bound, so I would call that a measurement. And if you add SKA and Euclid, you can define it even better, so that measure it even better. Okay, so I think this is very spectacular kind of finding if it happens, because not only can we constrain the reheating temperature, which is a very important parameter in particle physics because it tells us about what kind of dark matter is possible, what kind of baryogenesis is possible, we also can possibly constrain a microphysical parameter, namely the inflaton coupling. So therefore, we can what I would call it is like we can connect cosmic inflation to particle physics, because we're constraining a microphysical parameter at extremely high energy scales that connects the inflation to an underlying theory of particle physics. So that's why I call it connecting cosmic inflation to particle physics. And I think it's, at least for me as a particle physicist, that would be a very spectacular result. That's also the context in which my daughter drew this picture for this announcement here. Okay, but of course, since I use this very basic, just saying, let me fit this with a Gaussian is of course a very paper-intensive theorist's approach. I'm a paper-intensive theorist by training, I did that, but of course no serious person working on cosmological data would believe such an analysis if it weren't backed up with a proper forecast. And our postdoc Isabel Oldengott has done that in a follow-up paper, and here you can see the same thing, the posteriors for the reheating temperature and the inflaton coupling. And this green line is for those fiducial volume my simple analytic method. And here, Isabel has simulated the sensitivity of Lightbird and CMBS4 with different assumptions. And you can see that the result that she gets is actually even better than what my own analytic estimate suggested. Isabel is much more skilled than I in running all these complicated software. So luckily we had her, and she did this very impressive analysis for us. And she convinced me that, and hopefully will convince the rest of the world, that these curves can be trusted, in spite of the fact that the initial version was obtained with a kind of very simple paper with pencil theorists. Yes. Okay, so that's, we did that is for the RGI model, and we did, for example, here the same thing for an alpha attractor model. Here we see a very similar thing, but we see in the alpha attractor model, we find that the peak of the posterior peaks in the region where we have feedback effects. So therefore, we can still measure the reheating temperature, but it is not obvious how to extract the inflaton coupling from that, because here, for this reheating temperature, you would have a strong parametric resonance, and this strong parametric resonance via rescattering of particles would in general make reheating, this effective damping parameter, sensitive to all the other parameters in the theory, which one would have to specify. It's still calculable in principle, but it's not so straightforward anymore to extract the constraint on the inflaton coupling. Okay, so that was the first example that I wanted to give to see how this kind of calculation of quantum field theory in the early universe can give you useful results that can be tested in future experiments, in this case, CMB observations. So take-home message, the future CMB observations do have the potential to constrain the reheating temperature, and if we are lucky, we have a situation like this, even the inflaton coupling within a given model of inflation, of course. Okay? So we learned something about particle physics. Yes? Is it trusted that? Okay. So here, the region where the feedback effects are, it means that nonlinear feedback effects and therefore dependencies on many parameters enter the duration of reheating. So there's no problem to have a parametric resonance as long as the wrong direction. As long as the parametric resonance doesn't terminate reheating. So for example, if you have this situation here you have non-perturbative effects, but the radiation still remains subdominant. So it means that the duration of reheating is not changed by the non-perturbative effect. So there's nothing wrong with having a preheating phase as long as the preheating phase is not efficient enough to terminate, like to finish reheating, right? Similar situation here with in this plot later, yeah? Here, in this plot with the thermal feedback. So here, this is the purely perturbative calculation, and here is the one including thermal feedback. Here, the thermal feedback happens at the beginning of reheating, but it doesn't change the duration of reheating. So in this case, we only care about nonlinear effects, feedback effects happening at the end of reheating, and that's what these conditions here are meant to guarantee, that it doesn't happen, and that's in this plot here. So this gray area means that feedback effects are likely to change the duration of reheating. So therefore, the duration of the reheating becomes sensitive, because when feedback effects kick in, suddenly the duration of reheating is sensitive to all parameters in the theory, because if your particles rescatter, and so then it depends via which gauge interaction, with which coupling constant, with which mass spectrum, then the gamma becomes a function of many, many parameters, right? So that happens in this region. So if you give me a specific theory, I can still, or somebody with a big lattice can still calculate the constraint in inflaton coupling in this region here, but you would have to specify the full spectrum of the theory with all gauge interactions and so. But in the white region here, the extraction of the inflaton coupling from CMB data is independent of the details of the underlying gauge groups and so that are coupled to. Does that make sense? Okay, so now I was a bit slower than I had hoped, but I hope I managed to get you impressed over this because I think it's really exciting. Now the second question that I want to briefly touch upon that can be treated with similar methods is baryogenesis. So the origin of the matter-antimatter asymmetry in the universe. So we know from observation that the observable universe basically contains no antimatter and a lot more photons than baryons. And the common explanation is that we started at some phase where there were a lot of matter and antimatter. And then when pair creation processes fell out of thermal equilibrium, there was a huge annihilation. And then the reason, so here yellow is photon and red is matter and blue is antimatter. Then there was basically everything annihilated into photons. And the reason why some matter is left is because initially there was a little bit more matter than antimatter, right? And how much a little bit more is has been observationally quantified in two different ways, either from the CMB and from Big Bang nucleosynthesis, and the two are in good agreement. It's order 10 to the minus 10. So it's only a very small fraction of matter. The excess of matter over antimatter initially was only very small. Still, it was not zero, and the question is, why was it not zero? Turns out the standard model cannot explain this, so we need physics beyond the standard model. And basically, as you may know, there are conceptually two popular explanations. So either there's a cosmic phase transition, such as during electric baryogenesis, or the decay of a heavy particle, which is, for example, the case in leptogenesis. And leptogenesis is what I'm going to focus on today. So the simplest incarnation of leptogenesis works in a model where you add to the standard model just a right-handed neutrino. That's all that is needed in principle to explain the light neutrino masses and leptogenesis. So if you add to the particle spectrum of the standard model, you fill these three gaps here with right-handed neutrinos, then you're done. This is sufficient to generate light neutrino masses through the so-called seesaw mechanism and do leptogenesis. Here, this is the Lagrangian that this corresponds to, and basically what you get is three mass eigenstates that are roughly the SU2 doublet with a small admixture of the right-handed state characterized by a small mixing angle, and this is the usual PMNS neutrino mixing matrix. And then you have three heavy states which are almost singlets and have a small interaction due to this mixing that generates the neutrino matrix. So theta is here mixing between the left and right-handed neutrinos, and that is what generates the neutrino mass matrix. That is, so here the right-handed neutrinos, they couple. Well, in the simplest model, this is the kinetic term for the right-handed neutrinos. Then they're coupled to the lepton doublet and Higgs doublet through a matrix F of U-cover couplings. So this is a matrix of U-cover couplings, and then they can have a Majorana mass. The magnitude of this Majorana mass is unknown. And because the light neutrino mass matrix is given by this combination here of the U-cover F and the Majorana mass, or likewise the mixing angle in the Majorana mass, cannot pin down the heavy neutrino mass by measuring the light neutrino properties because it's only given by this combination here, right? So this is unknown parameter, and in principle, you might believe it's at the gut scale, you might believe whatever, but phenomenologically, it can be anywhere between the pion mass and the gut scale. Okay? It can be as low as 100 MeV. Now, this seesaw mechanism can, at the same time, gives these neutrino masses, and the very same particles, the very same heavy neutrinos could do leptogenesis if these heavy mass eigenstates decay in the early universe in an asymmetric way. So this is the standard picture established by Fukugita Yanagida in the 80s. So it's a very simple idea. We have these heavy mass eigenstates n that exist in the early universe. They can decay into Higgses and leptons. And at tree level, the probability to decay into matter and antimatter is the same. But if we form the interference with the loop corrections, then you can have a situation in which they preferably decay into antimatter. Then all what you have to do is you have to have a population of these guys in the early universe. They decay, and you have more matter than antimatter because they preferably decayed to matter. Okay? So practically, this process is typically described with this very simple Boltzmann equation, where Yn is the abundance of the heavy neutrinos in the plasma, and Yb minus L is the matter-antimatter asymmetry. This is a simple two-coupled differential equation, and when you solve them, you get something like this from this paper here. This is time, this is the abundance, and the heavy neutrinos start from zero, they get produced, they approach thermal equilibrium, then they freeze out and they decay, and in this non-equilibrium dynamics produces this non-zero asymmetry. But in reality, the system is a lot more complicated because we know we have 3 heavy neutrino flavors, and we have 3 standard model flavors, so they have flavor effects. And in addition to that, of course, I'm personally most interested, I should say, in the realizations of this idea where the heavy neutrinos are light enough that I can detect them in a collider. Okay? So if I want these heavy neutrinos to have masses below the TeV scale, then in order to still have small neutrino masses without fine-tuning and to get leptogenesis successful, I need that they have quasi-degenerate masses. And if they have quasi-degenerate masses, the final asymmetry becomes sensitive to the thermal screening effects in the plasma, because the effective mass splitting can be affected by screening effects in the plasma. So it is very desirable to understand this process not in this ad hoc Boltzmann equations, but from first principles. So what do? Well, we go back to the Schwinger-Keldysh formalism, and we again start with the 2pi effective action. We write down the Kadanoff-Bohm equations. Again, the Weidmann functions here, or we can form the spectral function and statistical propagator, this time for fermions. They again fulfill this kind of non-local equations where this is the spectral function and the propagator, just like we had for the scalar before. And on the right-hand side, we have the non-local term with some kind of self-energies. Now, I'm already towards the end of my talk, so I'm not going to spend as much time on discussing the validity of various approximations as I did in the first part. But again, what you do is you do a systematic derivation until you find quantum kinetic equations that capture the relevant part of the dynamics. Of course, these approximations in this case will be different than in the case of inflation and reheating because we have a different physical system. So what you do in this case, because we don't have a background field here, we can go to Wigner space, then we can do a gradient expansion to obtain Markovian equation of motions. We identify the spectrum from the poles of the propagators, write down quantum from that by putting then the correlation functions on shell onto the quasi-particle poles. We can find quantum kinetic equations for effective quasi-particle distribution functions. We can calculate the coefficients in thermal field theory in this case, because here we're having a system that is very close to thermal equilibrium. The rest of the primordial plasma is in thermal equilibrium. Only these heavy neutrinos are out of equilibrium. So I can use thermal quantum field theory to calculate the coefficients, and then I do some suitable momentum averaging. If that was too fast, then I would like to refer you to this review written by my collaborator, who has written a whole review about this kind of methods, how to get from the Schwinger-Dyson equation in the closed path formalism to effective equations that can be used to do leptogenesis. So instead of going through the steps in the systematic derivation in detail, I want to show you what kind of equation you get in the end. So this is a type of dynamical equation that you need to solve to reliably calculate the baryon asymmetry. So here, these are the chemical potential or the matter-antimatter asymmetries in the three lepton flavors, E, mu, tau. Those are three equations. And then you have density matrix equations for the heavy neutrinos and heavy antineutrinos, because, well, they're Majorana particles, but for the two helicity states of the heavy neutrinos. And these effective kinetic equations can be written in terms of some Hamiltonian, a commutative of the Hamiltonian. Just if you know the solar neutrino problem, you might know the density matrix equation for the solar neutrino problem. This is the same thing for heavy neutrinos. Then there are various different interaction rate, lepton number containing one, lepton number violating one, and chemical potentials in the plasma and distribution functions. So all of this can be systematically calculated using this procedure. So if you have ever worked on the solar neutrino problem, or seen this is basically a very similar equation, also the density matrix equation. And these effective Hamiltonians here include so-called potentials that the heavy neutrinos experience in the primordial plasma, which is another way of saying that the dispersion relations are being modified by the presence of the plasma. And it turns out you actually see very similar effects to what you see in the solar neutrino problem. So if you know the solar neutrino problem, you might know the MSW resonance. That gives you a very efficient conversion of different neutrino flavors into each other. And here you see something similar. So these are the eigenvalues of the effective Hamiltonian as a function of time. And you can see here this avoided crossing that you see here is basically the same thing as what you saw in the solar neutrino problem, but it's the MSW effect in the solar neutrino problem. Just here it happens in the early universe, and it happens among stereo neutrinos. And what it does is it leads to a resonant, dynamical resonant enhancement of the production of matter-antimatter asymmetries. And all of this, the reason why I'm showing this to you is none of this is captured by the standard Boltzmann equation. Seeing these effects that greatly enhance the asymmetry, so this is the asymmetry in the active and like in the normal neutrinos and the heavy neutrinos as a function of time, all these effects really do impact on the final asymmetry. So if you say, I'm overdoing things with the string formalism, including all these meta corrections and so finite medium corrections, so it really is necessary to find the final asymmetry, the correct value of the final asymmetry. So using this relatively formal non-equilibrium quantum field theory methods to describe this process has an asset because, at least in these low-scale scenarios, it gives you a possibility to get all the relevant corrections from the mean thermal, right, to calculate the final asymmetry. And that's what you want to do to make predictions for our friends from collider physics, right? So this is my final plot. I think I'm also reaching the end of my time. In which I compare the parameter space that is, so this is the mass of this hypothetical heavy right-handed neutrino that exists, and this is this mixing angle. So this mixing angle u squared characterizes its interaction strength with normal matter relative to the interaction strength of the weak interaction. So if you were at u squared equals 1, this heavy neutrino would interact roughly as strongly as a normal neutrino. The further you go down, the more strongly these interactions of the heavy neutrino are suppressed compared to those of the normal neutrinos. And then you see in this plane, this is the mass. It goes up to like TeV, 10 TeV. Down here, you're excluded by failing to explain the light neutrino oscillation data. Up here are experimental searches. This, for example, is this is CMS, and this is also CMS, I think. This is electric precision data here. These are beam dump experiments with mesons. Okay, so everywhere in the white area, you're able to explain the light neutrino masses through the seesaw mechanism. And between the black lines, you can explain the baryon asymmetry of the universe. So for the solid black lines, if you assume that there are no heavy neutrinos in the early universe to begin with, so they first have to be produced from the plasma. And for the dotted line, if you start with a thermal abundance, so two different sets of initial conditions. And then all the colorful lines are the sensitivities of proposed future collider experiments that can look for these heavy neutrinos. And the great thing is we find in this paper here, we find this huge parameter space for leptogenesis works. In order to do this, as I said, it was crucial to do the calculation in the early universe properly and include all sorts of quantum statistical effects to use sort of first principles methods. And there is a real chance to discover these particles at the collider. And what I can't talk about today, but I'm happy to tell you if you're interested, is apart from just showing that leptogenesis is possible in this parameter space here, based on the leptogenesis calculation, we can also make predictions for the properties of these heavy neutrinos other than their overall mixing. Okay? And if you discover them at collider, these kind of properties can be measured, and it can be, well, this is a testable model of neutrino masses and leptogenesis. Okay, so yeah, these are my conclusions. I gave two examples for, first of all, I believe that the early universe provides an excellent laboratory for fundamental physics in regimes that are hard to test in the laboratory. Second of all, I believe that it's very important to develop computational techniques that allow us to, from first principles, describe the interactions of particles in such an extreme environment. And then I gave you two examples where it was necessary and beneficial to apply these first principles techniques to simulate processes in the early universe in order to make predictions that can be tested either in cosmological observations in case of the CMB or collider experiment, cosmological observations in case of reheating and its signature in the CMB, or collider experiments in the case of leptogenesis and the possibility of discovering the heavy neutrinos at colliders. Okay, I hope I've convinced you that the early universe is a great laboratory for fundamental physics, and we need theorists doing calculations in non-equilibrium quantum field theory from first principles to get reliable results that can be tested in experiment. Okay, thank you very much. Well, you're the chairman.
Thanks for your talk. When you are adding these interactions to inflaton, is the theory normalizable?
So in our paper, we considered. So I looked at it somewhere here. So in order to do this analysis, of course, you have to specify the model of inflation, and you have to specify the interaction that you want to constrain, right? But the constraint doesn't change so much. So here we looked at difference. So this is non-renormalizable, and these three are renormalizable. So we considered both. So this is renormalizable scalar interaction, also renormalizable. This is U-cover interaction with fermions. So this is a coupling to axial to gauge F-mu tilde axion-like interaction. So this one is non-renormalizable. These three are renormalizable.
Actually, what's the value of the cutoff?
So so it turns out that the combination. So for what we did, we didn't need to specify as long as the cutoff is. All we have to make sure is that this cutoff is not lower than the reheating temperature. Than the temperature in the early universe, right? Because if you go to these plots that we made here. Oh no, I'm going the wrong direction again. So here what I wrote is the inflaton coupling. So this is the U-cover coupling. That is by construction dimensionless, right? What I did in the situation where we have where we have a dimensionful coupling, here you can construct dimensionless quantity that is composed out of the sigma and the inflaton mass, and you can express it in terms of that. So this quantity that would appear at the y-axis is, it's basically the sigma. It's just a dimensionless combination of the sigma and the inflaton mass and this lambda, right? So that's the parameter you constrain. And then how that translates into lambda, of course, depends on what potential, inflaton potential, because you construct dimensional combination of this lambda and the inflaton mass and the sigma. That's the quantity that you constrain. So what's the cutoff on lambda? So what's the value of lambda depends on what's your inflaton mass. So that depends on your inflationary potential. But you see what I mean? So there's no universal answer to this. It depends on your inflationary potential. What you have to do for self-consistency is, of course, you have to make sure that this lambda is large enough that during reheating the validity of effective field theory approximation doesn't break down. Okay, does that answer your question?
Thank you.
Okay, I don't know if that was the most straightforward way to answer your question, but
More questions? I hope just in this page, why there's no square here? Usually there's a 1 minus 2 m cap. It's a 5 decay into it's a 4D decay.
yes, there should be. Maybe it's a type.
Yeah. And yeah, all these places there should be a square.
It could be. It could be that there's a typo. Yes.
Yeah.
It's true that usually it's a square. It's true.
Okay. So
Can you go back to that US squared m plot for the neutrino, the heavy neutrino mass?
At the end.
Yeah.
Sorry, I'm always going the wrong way. And I'm really not learning from my mistakes.
Yeah, so there are two black lines here. Why is that?
So that depends on the initial condition. So if you assume that initially you set up your initial condition at very high temperature, there are no heavy neutrinos. You can say they're gauge singlets, so they're just not there in the beginning, and then they have to gradually approach equilibrium. Mm-hmm. And then they freeze out and decay later, but they first freeze in and then they freeze out. Then you are between these two black lines. And the simple understanding is that, the Sakharov conditions.
Are you saying you're between those two?
Between them, yeah. Anywhere between them you can be. Anywhere between them gives you successful leptogens. This is a two-dimensional projection of an 18-dimensional parameter space, right? So there are 18, in the model with 3 heavy neutrinos, there are 18 parameters in addition to the standard model. So this is a two-dimensional projection of an 18-dimensional parameter space. So that means anywhere between these two lines, there exists a combination of parameters that is projected onto this plane that gives you the right asymmetry, okay?
Mm-hmm. But the other lines from experiments...
And sorry to answer your first question, this other black line assumes thermal initial conditions. So for example, if there's grand unified theory, and they have some kind of, or even left-right symmetric theory, and they have some kind of gauge interactions at high temperature, you would not expect them to start theory, you would expect them to thermalize early, So that's that. Okay, sorry, now you wanted to ask something about
So the experimental lines, are they like upper limits or lower limits? What are they?
Inside, so the lower you go, the harder it is to test, because this gives you the interaction strength of the heavy neutrino relative to the weak interaction. So up here is already excluded, and here you see, so LHC, for example, will be able to do everything inside this, will be a displaced vertex search. This will be prompt searches that will be able to exclude all of this, and discover, hopefully, not just exclude. So this is displaced vertex search at LHC, prompt searches at LHC. There are different kind of searches you can do. And you can see, I was giving a talk on the weekend about this CEPC in China would actually be a very, so just for some advertisement for, I'm not only a cosmologist, I also like collider physics. So CEPC, so this is what CEP zero pole run can do, can produce 100,000 events if we're lucky. If you are high up in this. This is the MU square plane, this is the sensitivity of CPC, and here you see how many events you can produce. You can maybe make 100,000 events and study properties of these particles in a lot of detail, and it's really testable. You can not only discover them, you can really learn. You have so many events, you can extract the parameters and plug them into quantum kinetic equations that I showed you and see if you get the right Byron symmetry,
So I have one more question. So if you go to the lower right part of that plot, you didn't have any constraints.
You mean not this one, but the
but
one.
I guess they're the same, right? So it's just large.
Well, here there are no constraints shown, so let me go.
You don't show any constraints.
So let me go here.
So is there any upper limit, anything that kind of limits this on the right-hand side if you go to very large?
Yes, so if you go up too far to the right corner, there are two things. At some point, you start, perturbativity breaks down because, there are two things. So one of them is perturbativity breaks down because you want this to be the perturbative expansion. And the other thing is that your corrections to the Higgs potential become large. So if you go too far to the upper right corner, you
Well, you cannot go to upper right because you're already limited there.
yeah, but only by electric precision data. What I'm saying is there are stronger bounds going like this later, stronger than, because electric precision, this is electric precision data. It basically stays flat. So your heavy neutrino mass is much larger than the Z-pole. Electric precision data is like a flat curve.
But the lower right, you said you can be arbitrarily heavy there.
Down here,
Yeah, you can go very to the right.
yeah, lower right, yes. So, but what you start having is then you start coming, at some point there's a line that comes from here that tells you the Higgs that you screw up the Higgs potential, right? But of course, then it depends on if you embed the whole thing into grand unified theory or in the supersymmetric theory, you might be able to fix that problem. But if you just take it as a standalone, just the seesaw Lagrangian without adding supersymmetry or so, then there will be a line that is not shown here that comes from here that tells you that you screw up the Higgs potential, and then because it has a steeper slope, it will eventually hit that line, you know?
Sounds good, thank you.
But it's way beyond current collider sensitivity, so it's a very theoretical bound, you know?
Okay, so let's thank our speaker again. And let's come back at 4:30. Right?